1. We are back at the starting point.
Okay, I think I'm going to stop. We won't go down because... Okay, so I wanted to say a little bit about the techniques. We hit a problem right away. The problem with gamma ray, building detectors for gamma ray experiments is that we have the atmosphere. The atmosphere blocks gamma rays, and so it's impossible to measure anything from Earth other than with indirect experiments. So we have two sources, two options open to us. One is we can build satellite experiments, launch them, and put them in Earth orbits. Problem is that these are expensive. The first one, the experiment that I worked on, was launched by the space shuttle. It's $500 million. It's very expensive to work on these experiments. What you see here is basically the atmospheric opacity as a function of wavelength. You can see that visible light makes it all the way down to Earth, radio waves, the gamma rays are blocked by the Earth's atmosphere. So in order to do any kind of science with gamma ray experiments, you build a satellite, and here what you see is an experiment called the Fermi gamma ray satellite. It was launched in 2008 at Kennedy Space Center. It's still in orbit. It's taking data. It's this beautiful experiment. I was there for the launch, except you can never time a launch. We were there, didn't happen, we came back, and then the launch can get scrapped last minute. It was a $100 million experiment. It's collecting data. The problem with the Fermi experiment is that it's not very large. You can't do, there's only so much that you can build and put up in space. The size of this experiment is about what we call the effective size is about this much. So you can't really do much astronomy with that. So instead, what we do is if you look at this picture, if you take a high energy gamma ray that comes into the top of the atmosphere, it creates a shower of particles, and as a result of the shower, you also see in these particles, as they travel very fast through the atmosphere, what you see is basically a shock wave that comes down, an optical shock wave in the form of blue light. And this light actually has a name. It's called Cherenkov Radiation. It was worked out by a Russian physicist. You see Cherenkov radiation, which is blue light, and we know, I'll show you a picture here. This is Cherenkov radiation that's measured in a French nuclear complex. What you see, you see Cherenkov radiation when you have a particle that's going faster than the speed of light in that medium. Okay, so right here, this blue glow is Cherenkov radiation that you measure, and you can think of this as a shock wave. So if you've seen ducks in a pond, you can see sort of a wake behind the ducks as they swim. You can think of Cherenkov radiation visually in sort of that terms. And what you can do then is, as the Cherenkov radiation comes to the ground, you can think of a flashlight. You take a flashlight and you shine it. You see light on the ground. You have a pool of light. You can put detectors in this pool of light and then indirectly measure that light. And here's actually a picture that kind of explains that better than I'm saying it. What we're trying to do is image this Cherenkov light. So you can take this light pool, you put a detector here. As the light comes down, it shines pretty much like a flashlight from the top. This pool is about 250 meters across. You can put a detector here. At the focal plane of the detector, you can build a camera. Okay, and in that camera, you can make sort of a pixelated camera. So it's pretty much like a digitized pixelated camera. And then you can image that light in the plane of that camera. And in the process, point back to, this is sort of a visualization of how we actually do the analysis. So we take, let's say, 3 telescopes like this, point back here, the intersection points back to the source. So by measuring, taking a picture of this image here, you can learn about where that source is coming from. Okay, so this is actually the detector that we have. This is in Arizona. This is called the VERITAS Cherenkov telescopes. It's in southern Arizona. It's about 30 kilometers north of the border. Sorry, you see this here? And you can see that there are 4 of these telescopes. This one here is the mirror. You can see zoomed in. The mirror is not one plain, fixed plane piece of glass. It's made up of these individual facets. joined together. And then at the focal plane of this camera, you see here is what we call photodetectors. And you can actually see a better picture over here. Each one of these is made up over here, and I actually have one here which I will ask the students to pass around. What you see here is a photodetector that we use in these. And these take about 500 million pictures per second. You digitize them, and then you try to do some image reconstruction to try to learn about the gamma rays. So there are several of these. There are actually 3 of these Cherenkov telescopes all over the world. The one that we are working on in VERITAS here in southern Arizona, and then there are 2 others, one in Spain and the other